What is your home address? While most people would reel out their postcodes without thinking about it, the most powerful telescope ever, the James Webb Space Telescope, has made a shocking revelation about our address. We have a bigger postcode and we are all existing inside a black hole. How did the Space Observatory come to this conclusion, and what does it mean for our knowledge of astronomy? Join us as we deep dive into the James Webb Space Telescope's shocking discovery that we live inside a black hole. Black holes are regions of space where gravity is so strong that nothing can escape, not even light. That means they're invisible to our eyes, but we can detect them by their effects on the surrounding matter. For example, some black holes have disks of gas and dust swirling around them at high speeds, emitting a lot of radiation. These are called quasars, and they are some of the brightest objects in the universe. But how do black holes form? Well, there are different types of black holes depending on their size and origin. The most common ones are called stellar black holes, and they form when massive stars die and collapse under their own gravity. These black holes can have masses up to 20 times that of our Sun, but diameters of only a few kilometers. But there are also much bigger and rarer black holes called supermassive black holes. These monsters can have masses of millions or even billions of suns and diameters of millions of kilometers. They are usually found at the centers of galaxies, including our own Milky Way. Scientists don't know exactly how they form, but they think they may have started as smaller black holes that merged with other black holes or stars over time. So how scary are black holes? Well, it depends on how close you get to them. If you stay far away from a black hole, you won't notice much difference from any other massive object in space. But if you get too close, things get weird and dangerous. The closer you get to a black hole, the stronger the gravity becomes, and the more time slows down for you compared to someone far away. This is called gravitational time dilation. It means that if you watch someone falling into a black hole, they will appear to freeze and fade away as they approach the event horizon, which is the point of no return. But what is really baffling about black holes is that some scientists claim that we are living right inside one. Let's go back in time. The Big Bang occurred before humankind existed, before Earth formed, before the sun ignited, before galaxies were created, and before light could ever shine. This took place 13.8 billion years ago. But what about prior to that? Many physicists believe there is nothing before that. They believe that time began to clock at the instant of the Big Bang, and that thinking anything earlier isn't scientific. We'll never know what reality was like before the Big Bang, what it was made of, or why it erupted to create our universe. Such concepts are incomprehensible to humans. However, some unconventional scientists disagree. These physicists believe that before the Big Bang, all of the newborn universe's matter and energy were compressed into an extraordinarily dense yet finite speck. Let us refer to it as the seed of a new universe. This seed is thought to have been almost impossibly small, potentially trillions of times smaller than any particle observed by humans. Despite this, it is a particle capable of triggering the creation of every other particle, not to mention every galaxy, solar system, planet, and individual. If you really want to label something the God particle, this seed appears to be an excellent candidate. So how does such a seed come to be? One theory advanced recently by Nicodem Poplawski of the University of New Haven is that the seed of our universe was fashioned in the ultimate kiln, most likely the most severe environment in all of nature, inside a black hole. Before we go any further, it's crucial to note that many theoretical physicists have come to believe that our universe isn't the only one. Instead, we could be a part of the multiverse, a vast collection of distinct worlds, each with its own bright orb in the genuine night sky. How or even if one universe is linked to another is the subject of much speculation, all of which is highly hypothetical and as of yet utterly unprovable. One intriguing theory, though, is that the seed of a universe is comparable to the seed of a plant. It's a bit of important material firmly compacted and hidden inside a protective shell. And this is exactly what happens inside a black hole. Black holes are the remains of massive stars. When a star of this type runs out of fuel, its core collapses inward. Gravity rips everything with an ever-increasing force. Temperatures can reach 100 billion degrees Celsius. Atoms are shattered, electrons are shattered, and those bits become even more crushed. By this stage, the star has become a black hole, which implies that its gravitational pull is so strong that no light can escape. The event horizon is the border between the inner and exterior of a black hole. And massive black holes, some millions of times the mass of the Sun, have been detected at the heart of practically every galaxy, including our own Milky Way. Now, if you use Einstein's ideas to compute what happens at the bottom of a black hole, you'll get an infinitely dense and indefinitely small spot, a hypothetical concept known as a singularity. In nature, however, infinities are uncommon. This discrepancy is due to Einstein's ideas, which provide fantastic computations for the vast majority of the cosmos, but tend to fail in the face of immense forces, such as those found inside a black hole or present at the creation of our universe. According to physicists such as Dr. Poplawski, matter inside a black hole can only be compressed so far. This seed may be exceedingly little, with the weight of 1 billion suns, yet it is real, unlike a singularity. And according to Dr. Poplawski, the compacting process comes to a halt when black holes spin. They spin at breakneck speeds, possibly approaching the speed of light, and this rotation gives the packed seed a tremendous amount of torque. So not only is it little and hefty, but it's also twisted and squeezed, like one of those corny spring-loaded snakes in a can, which can unexpectedly unspring with a bang. That's a big bang, or as Dr. Poplawski prefers to call it, the big bounce. In other words, a black hole may be a conduit, a one-way door, as Dr. Poplawski puts it, between two universes. This means that if you fall into the black hole at the center of the Milky Way, you, or the shredded particles that were once you, could find yourself in another universe. Dr. Poplawski adds that this other universe isn't within ours. The hole is just a link, like a shared route connecting two aspen trees. But what about the rest of us here in our own universe? We could be the offspring of an earlier cosmos. Call it our mother galaxy. This mother universe's seed may have had its great bounce 13.8 billion years ago, and even though our universe has been quickly expanding since then, we may still be concealed behind a black hole's event horizon. And now, what is very remarkable is the latest discovery by the JWST of a cosmic monster of a black hole which is 10 million times heavier than the Sun. But not only is this black hole massive, it's the earliest known black hole in the universe. The supermassive black hole with a mass 10 million times that of the Sun was discovered at the center of a young galaxy 570 million years after the first began by the JWST, whose powerful cameras allow it to see back in time to the earliest phases of the cosmos. The cosmic monster could be one of the numerous black holes that gorged themselves to ever larger sizes during the cosmic dawn, which began approximately 100 million years after the Big Bang and lasted 1 billion years. Astronomers don't know why there were so many of these black holes or how they grew to be so massive. This is the only one that we've discovered at this redshift, that is, a point in time after the Big Bang, but there should be many more. This is according to scientists who believe that this black hole did not form recently, so there should be others that are younger and existed earlier in the universe. We are just getting started with the JWST and studying this period of cosmic history in this way, and they are excited to find more of them. Black holes are formed by the collapse of massive stars and grow indefinitely by feasting on gas, dust, stars, and other black holes. Friction leads the material spiraling into the gluttonous space-time ruptures to heat up, and they generate light that can be observed by telescopes, transforming them into so-called active galactic nuclei, or AGN. The most extreme AGN are quasars, which are billions of times more massive than the Sun and release their gaseous cocoons with light blasts trillions of times brighter than the brightest stars. Now, because light travels at a constant speed through space, the deeper scientists search, the more distant light they intercept, the further back in time they view. The astronomers search the sky with two infrared cameras, the JWST's mid-infrared instrument, MIRI, and near-infrared camera, then use the camera's built-in spectrographs to break down the light into its component frequencies to find the black hole. They discovered an unexpected increase among the frequencies included within the light by dissecting these small glimmers delivered from the cosmos's early years, a critical clue that the heated material surrounding a black hole was blasting out faint traces of radiation across the universe. It's unclear how black holes appeared so abruptly over our young cosmos. Astronomers are still looking for even younger, hypothesized primordial black holes, however, that formed very soon after or possibly before the Big Bang, according to some hypotheses. However, they have been elusive thus far. There are two leading theories for how so many black holes formed so quickly after the Big Bang. They are the remains of giant stars that formed much faster than the ones we know today, or they are billowing clouds of incredibly dense gas that collapse suddenly to form the all-consuming singularities in space-time. The direct collapse method would have to start with a larger amount of matter in the galaxy collapsing directly into a black hole. It's less likely, but it would take less time, and there hasn't been that much time since the point at which we observed it. More likely, however, a population 3 star, a category of hypothesized stars that were the first to ever exist in the universe, were made of only hydrogen and helium, exploded and left behind a black hole around 200 million years after the Big Bang, and then accreted a lot of material pretty quickly and occasionally at a faster than stable rate to swell up to the size that researchers observed. The researchers will now begin scanning for an even stronger signature of light from the distant galaxy with the team who created MIRI. These emissions could hold more information about how the mysterious black hole at the galaxy's core arose. And prior to this, the JWST caught two galaxies merging around a monster black hole. The cluster of galaxies was detected merging around a rare red quasar, a monster supermassive black hole that is greedily feeding on gas and other stuff. A multinational team of scientists made the stunning discovery while looking back billions of years with the JWST. The discovery provides an opportunity to study how early galaxies collided to generate the cosmos we know today. The SDSS J165202.64 plus 172852.3 quasar, which is blindingly brilliant and highly red, is roughly 11.5 billion years old and one of the most powerful ever seen from such a great distance away, according to the researchers, who describe it as a black hole in formation. The scientists believe something dramatic is about to occur in these systems. The galaxy is at a critical juncture in its evolution, about to transform and look completely different in a few billion years. Earlier, Hubble Space Telescope and Gemini North Telescope in Hawaii scans of this region of space identified the quasar and hinted at a galaxy in a transitional phase. However, it wasn't until later observations with the JWST revealed not one, but at least 3 galaxies spinning around the quasar. The scientists thought they found clues in previous photographs that the galaxy was likely interacting with other galaxies on the way to a merger because their shapes get altered in the process, and they thought they saw that. However, when they received the JWST data, they had no idea what they were even looking at, and they spent several weeks simply looking at the photographs. The JWST photos of the region also revealed that the three galaxies are traveling extremely swiftly, implying the presence of a massive mass, leading scientists to believe that this could be the densest area of galaxy formation ever observed in the early universe. Even a dense knot of dark matter isn't sufficient to explain it. The team believes we are witnessing a region where two massive halos of dark matter are merging. Even members of the team who had envisaged witnessing this quasar with JWST as recently as a decade ago were surprised that the Space Telescope, which only began relaying science photos back to Earth in July, obtained such clear views of the region. The researchers will now seek to follow up on this surprising galaxy cluster in the hopes of unraveling the mysteries of how such tight clusters of galaxies evolved in the early cosmos and how this process is affected by the supermassive black holes that lurk at their centers. They tell us that what we see here is only a small subset of what's in the dataset. They said there was just too much going on here and that they started with the biggest surprise. Every blob here is a baby galaxy merging into this mother galaxy, and the colors represent different velocities, and everything is moving in an extremely complicated way, but we can now begin to unravel the motions. The JWST continues to shed light on celestial bodies as it reveals never-before-seen details of the evolution of galaxies and black holes, and it recently revealed the Stephan's Quintet in a new light. This massive mosaic, which covers roughly 1/5 of the Moon's diameter, was the JWST's largest image to date. It has about 150 million pixels, is made up of nearly 1,000 different image files. The findings shed new light on how galactic interactions may have influenced galaxy evolution in the early cosmos. Stephan's Quintet was discovered in 1877 by French astronomer Edward Stephan in the constellation Pegasus. JWST's strong infrared vision and exceptionally high spatial resolution revealed previously unseen characteristics in this galaxy group. The image is adorned with sparkling clusters of millions of newborn stars and starburst regions of new star birth. Gravitational interactions are pulling sweeping tails of gas, dust, and stars from many galaxies. The JWST captured massive shockwaves when one of the galaxies, NG 7318b, smashes into the cluster. The 5 galaxies of Stephan's Quintet are known collectively as the Hickson Compact Group 92 or HCG 92. Despite being referred to as a quintet, only 4 of the galaxies are genuinely close together and engaged in a cosmic dance. When compared to the other 4, the 5th and leftmost galaxy, NG 7320, is well in the foreground. NGC 7320 is located 40 million light-years away from Earth, whereas the other 4 galaxies, NGC 7317, NGC 7318A, NGC 7318b, and NGC 7319, are located approximately 290 million light-years away. And yet, from a cosmic perspective, this is still quite close when compared to more distant galaxies at billions of light-years away. The study of such neighboring galaxies helps scientists better grasp features found in a much larger universe. This proximity gives researchers a front-row seat to the merger and interactions between galaxies that are so important to galaxy evolution. Scientists seldom see in such detail how interacting galaxies stimulate star formation in one another and how the gas in these galaxies is disrupted. Stephan's Quintet is an excellent laboratory for examining these fundamental dynamics of galaxies. Now, tight groupings like this one may have been more common in the early cosmos when superheated in falling material powered very active black holes known as quasars. Even today, the group's top galaxy, NGC 7319, contains an active galactic center, a supermassive black hole 24 million times the mass of the Sun. It aggressively attracts material and emits light energy equivalent to 40 billion suns. JWST used the NIRSPEC and MIRI to study the active galactic nucleus in exquisite detail. The Webb team received a data cube or collection of photos of the galactic core's spectral features from the Sensors Integral Field Units or IFUs, which are a combination of a camera and a spectrograph. The IFUs, similar to medical magnetic resonance imaging or MRI, allow scientists to slice and dice the information into multiple images for further analysis. JWST peered through the dust shroud surrounding the nucleus, revealing hot gas near the active black hole and measuring the velocity of brilliant outflows. The telescope observed these outflows caused by the black hole in unprecedented detail. The JWST was able to resolve individual stars and even the galaxy's luminous core in NGC 7320, the visual grouping's leftmost and closest galaxy. JWST also showed a large sea of thousands of distant background galaxies similar to Hubble's deep fields. The data from JWST, when combined with the most detailed infrared image of Stephan's quintet yet obtained from MIRI and the NIRCam, will provide a wealth of vital new information. It will, for example, aid scientists in understanding the rate at which supermassive black holes feed and grow. And the JWST also detects star-forming areas considerably more directly, and it can investigate emissions from dust a degree of precision previously unattainable. But perhaps more surprising is the link found between black holes and one of the most mysterious things ever discovered in the universe, evidence that black holes are the source of dark energy. Observations of supermassive black holes in galaxies' centers indicate a possible source of dark energy, the missing 70% of the cosmos. The results from ancient and dormant galaxies suggest that black holes are expanding faster than expected, which corresponds to a phenomenon predicted by Einstein's theory of gravity. As a result, nothing new has to be added to our understanding of the cosmos to account for dark energy. Black holes, together with Einstein's gravity, are the source. A team of 17 academics from 9 nations led by the University of Hawaii and including Imperial College London and STFC RAL space physicists came to this result. The findings were reported in the journals the Astrophysical Journal and the Astrophysical Journal Letters. This is a really surprising result, study co-author Dr. Dave Clements of Imperial's Department of Physics remarked. We began by studying how black holes evolve over time, and we believe we've discovered the solution to one of cosmology's most difficult challenges. If the theory holds, then this is going to revolutionize the entire field of cosmology because we finally have a solution for the origin of dark energy, which has perplexed cosmologists and theoretical physicists for more than 20 years. It was discovered in the 1990s that the expansion of the cosmos is accelerating. Everything is moving away from everything else at an increasing rate. This is difficult to explain because the gravitational attraction of all objects in the universe should be slowing the expansion. To explain this, it was proposed that a dark energy was pushing things apart more forcefully than gravity. This was related to an idea developed by Einstein but later abandoned, a cosmological constant that countered gravity and prevented the cosmos from collapsing. The discovery of the rapid expansion of the cosmos, with its main component being a type of energy included in space-time itself, called vacuum energy, resurrected this concept. This energy pulls the cosmos apart, hastening its expansion. However, black holes pose a challenge since their extraordinarily intense gravity is difficult to oppose, especially at their centers when everything appears to break down in a phenomenon known as a singularity. The new finding indicates that black holes gain mass in a manner compatible with their possessing vacuum energy, providing a source of dark energy and eliminating the requirement for singularities to form at their centers. The result was reached after researching the evolution of black holes over 9 billion years. When enormous stars reach the end of their lives, black holes develop. They are known as supermassive black holes when they are discovered at the centers of galaxies. These contain millions to billions of times the mass of our Sun inside them, resulting in extraordinarily powerful gravity. Black holes can grow in size by accreting matter, such as consuming nearby stars or by merging with other black holes. The researchers examined data spanning 9 billion years to see if these processes alone could account for the emergence of supermassive black holes. The researchers focused on a type of galaxy known as giant elliptical galaxies, which evolved early in the universe and then went dormant. Dormant galaxies have completed star formation, leaving little material for the black hole at their center to accrete, implying that any future development cannot be explained by standard astrophysical processes. When distant galaxies, when they were young, were compared to local elliptical galaxies when they were old and dead, the observed growth was far larger than predicted by accretion or mergers. Today's black holes are 7 to 20 times larger than they were 9 billion years ago. Further studies using similar populations of galaxies at different times in the universe's evolution reveal that the size of the cosmos and the mass of the black holes are in good agreement. These results suggest that black hole vacuum energy can account for the observed amount of dark energy in the cosmos. This is the first observational proof that black holes contain vacuum energy and are connected to the expansion of the universe, gaining in mass as the universe expands, a phenomenon known as cosmological coupling. If additional data support it, cosmological coupling will reshape our understanding of what a black hole is. We're really saying two things at once. There's evidence the typical black hole solutions don't work for you on a long time scale, and we have the first proposed astrophysical source for dark energy, said study first author Duncan Ferrer, a University of Hawaii astronomer and former Imperial PhD student. What this means is that while other people have proposed sources for dark energy, this is the first observational paper in which the researchers are not adding anything new to the universe as a source for dark energy, but simply exposing that black holes in Einstein's theory of gravity are the dark energy. What do you find fascinating about black holes? Let's hear your thoughts in the comments section below.